I'm going to talk about, well, I don't know what a good way to describe what I'm going to talk about is. I'm going to talk about stuff that Rust does, that the Rust compiler does, or really that the way that the language designers thought about things, mostly around memory management, but it's also got to do with data races. So I'm going to focus more on it's not even necessarily memory management, it's really resource management generally. So it's broadly applicable to, both allocating and deallocating memory, but also to opening and closing files and network sockets and whatever else you want. And all of the properties that they want to enforce are interesting both in terms of preventing space leaks and also in terms of preventing use after free and preventing uninitialized memory and preventing all of those things, but also in terms of preventing like accessing from two threads in a way that you didn't expect and all of that. So that's fun. So there are several different ways that this problem has been approached over time that are not the ways that I will talk about, although some of them are the ways that I will talk about. So for example, if you're just writing assembly code, then the approach is that you do it. There you go, you did it, now you're done. If you go to C, then you get a little bit better. The compiler figures out how to handle the stack for you, or whether or not you should have a stack, etc. Probably you should have a stack. Just that's a spoiler. You should have one of those.
The language semantics requires something that has the formal behavior of a stack.
That's right. and then they handle everything that you put on the thing with the behavior of a stack in a well-defined way, or a mostly well-defined way, and then that's good. And then if you want to do any resources that are not the resources on the stack, such as heap memory or files or network sockets, then you have to do all of your allocation and deallocation yourself manually and just hope that you did it right. Or if you just did it right, obviously. So it's fine.
That's not completely true.
And similarly for your data races, you put in all your locks, or hopefully not locks because you're a smart person, but whatever you put in, and then everything's good. Right? So that's like that's like the one step. And then people thought, or some people, who knows who these people were, they thought that they didn't like that, where they had to do most management themselves. So they immediately thought that they should come up with a silver bullet. I don't know why, but probably in every field, but especially in software and computer science, people are really interested in silver bullets. No one wants to think to themselves how we should break down this problem and solve all the small problems. We'll just something that will solve everything. So the most popular silver bullet is a garbage collector. And a garbage collector, you just allocate stuff as much as you want. You just like, if I got my heap up here, I'm like, I'll get a chunk of this, and I get a chunk of this, and then I'll like open a file over here, get my file handle going on. I just like do this, and I've got my pointers on the stack, so they inherit this stackish concept from the C because at this point literally everything is C, even if it isn't. And then you're like, oh yeah, this thing actually allocates some stuff inside of it, but you don't even know about that, and you make a giant mess, and then you've got some stuff that you allocated before over here, and they point to each other, and everything's a big mess. You just do this, and then from time to time, your program just stops doing whatever you told it to do, and looks at all of the memory and says, okay, well I got a pointer to this, and to this, and to this, and these are pointed to by this, which is pointed to by this, and these are, I don't need those. So we'll get rid of them. Okay, good. And then it keeps running your program. That's a garbage collector. It just periodically says, wait, I gotta delete some things, and then later on, you stop having access to this file, and it'll do the same thing, right? Close the file. And there you go, silver bullet. Now you never have any resource problems ever again, because it will just find all of them for you and stop you. It doesn't help you at all with your data races, not even close. It doesn't even try. In fact, it can cause some new ones, which is fun. But as long as you didn't kill the threads, everything has only one core, right? Where it's fine. Why would you have multiple cores in your computer? Are you on some kind of massive server? It's all fine. So we'll simply do it this way. And you didn't need your program to spend all this time running on the CPU. That would be ridiculous. It's lots of CPU cycles. We can use some of them doing this, so it's also fine. And everything's good. So that's still to date the most popular way to solve the resource part of this problem, where they just scan over and over again. But people don't like it in a theoretical sense, just because it's literally not a solution to the problem. It's just saying, oh, screw the problem. We'll just periodically mop up after ourselves instead of thinking about the problem at all. So theoretical people don't like this solution. And there are a lot of pragmatic cases where it doesn't help, like with when you're sharing stuff between threads, there can be a lot of extra complexity there, and when you're trying to get any kind of performance out of your system, then this obviously doesn't work, and it's bad things. So one of the other sort of bugs that people like to talk about a lot, especially people who have more of a theoretical background, they like to talk about regions and region inference because it's super fun and it sounds like it solves all your problems. And maybe it does, but no one has managed to make it work. So at least work well enough. There's like a implementation of Haskell that uses this that works pretty well, but I don't know. So the idea with region inference is basically that your whole program has like an entry point, and then you allocate some things. It's very stack-like, where you keep allocating things, but the difference is that instead of it being in a strict stack where as soon as I leave here, where I can only have one thing in here, I can have a function call in here, where I would have allocated things here, but I'm going to use them later, so I put them up there in the region that I've allocated, and then I keep going, and then when this returns, it's okay, because they're all up here. So we're kosher. And then when I come back up here, then we free all of that stuff. So that's regions, and region inference is basically various algorithms people have proposed to try and figure this out for you. Yeah. So that seems good because your data only lives as long as it needs to. Basically, the biggest problem with the region inference algorithm, all the ones that exist, is that they have you definitely can't infer a region that is too small, or you will have to use vector free. So you're going to err on the side of making your regions too tall, and then you will leak the data. But it's not really a leak in that it does get freed eventually, unless it assumes this fate. So it does get freed eventually, but often it stays around longer than it ought to have. But you don't have a lot of the problems a garbage collector has, where you can pop back up. And then I guess I should talk about ref counting, because I'm going to talk about that later, which is basically where you do the same kind of thing as with garbage collector, but you just like write down, instead of looking for all the pointers every time, you just write down inside of it how many pointers you have, and then every time you make a new one, you put the number up, and every time you get rid of one, you put the number down, and if the number is 0, then you erase the number. So this works pretty well. It has a couple of downsides. One is that you have to keep incrementing and decrementing these useless numbers all the time, which means it takes a little bit more space, which is not usually people's problem. It takes extra instructions every time you want to make a pointer, which seems like you thought you were making a pointer to a thing, not allocating anything, but suddenly it has to take all of these instructions. And also, your deallocations are non-deterministic.
Instructions are cheap. The main cost is memory references.
Sure, the memory references are definitely bigger, and also
and failure to collect cycles.
Yeah, well, I was going to talk about failure to collect cycles, but the non-deterministic deallocation is also a problem in real-time environments where you don't know as a programmer when deallocation will occur, and deallocation can be expensive.
You don't know how much you're going to need to deallocate when you drop a reference.
But you also don't know when, because sometimes when you drop a reference, nothing needs to be deallocated, and sometimes all of it does. Yes. So I guess that's true. Yeah.
You know that a thing will be deterministically deallocated as soon as you don't need it.
It's deterministic from the machine's point of view, but from the programmer's mental model, you don't know where in your code it will happen. Because if you knew where in your code it would happen, you would have just put a manual deallocation there, and why would you even do this? Because so the assumption is that you don't know. And then yes, like Dave said, you have this one where they point at each other, and now this one has one reference to it, and this one has one reference to it, and no one points at either of those, but they just hold on to each other forever. Yeah. So those are like the normal ways of that people solve these kinds of problems. None of these solve data races either. In fact, all all of them make data races worse. Every single one of them, right? Because here you've got this big chunk of shared memory instead of just sharing individual chunks. You've got to deal with this whole big thing that is going to be entirely freed or not. So your inference engine has to deal with, if you're sharing this thing among multiple threads, then it has to go up even higher or something, or in a different region that's shared among the threads, right? That's a big mess. This thing, you're incrementing and decrementing these counters all the time. So if you're sharing across threads, you've got to put a lock around just creating a pointer, which is insanity. Like, all of these things make data races worse. So none of them even pretend to solve that. And then they all have various problems. So what Rust does is none of these and all of them. Rust, in my estimation, has a tendency to take the opinion that the programmer should do what the programmer thinks is the right answer. And it'll just give you the tools you need to do that with. So Rust, you can do manual, same as C, manual pointers, manual allocation and deallocation, all that stuff. I'm not going to show that. It's not particularly idiomatic in Rust, but you can do it. I have done it. So I'm just going to, is there anything in my README that I can talk about? Stacks. Yeah, I talked about all of those. Yay! Okay. So here's a Rust program. It's not a very good one. Here I have my main function. And I'm going to take this string, you don't have to worry about it. So this toString is just because string literals are things, because string literals are not the same things as heap allocated strings. So I just say, like, get the string literal and box it out, basically, for the purpose of the example. I put in this variable, okay? And then I call the example, which does nothing, with S. And this compiles. You will be shocked, I'm sure, to see that this compiles. Yay! It has a warning because I don't use a variable, but whatever. What's interesting is that this does not compile. So it says I've used the moved value S. So this is the first thing, is when I take this S and I pass it here, this function, we say, takes ownership of the pointer. Or it doesn't have to be a pointer, but whatever, of the thing, which in this case is a pointer. And now example owns it, which means that this reference here, this name that was referencing that same pointer, is invalid at all locations that come after this. Statically invalid, the compiler fails. So that means that we don't have. This is largely a data races thing, but it's also a resource management thing, right? I can't accidentally share things, basically. I can share them on purpose, we'll see that later, but I can't ever share things between two threads or two closures or two end things accidentally. I can't store a pointer to one thing in two different data structures, none of that. Accidentally, I can't. Because it will be statically checked that I did not do it. Memory always moves. So that's fun. But now this one, I wanted to go here first. This one looks the same. It's exactly the same looking, except that instead of a string, I'm using an int. And I call the thing twice. And it's just a sign in here, call the thing twice, something weird up here. And you'll note that it compiles. So what's up with that? So this is, so there's a trait system in Rust, which is like type classes in Haskell, or like, I guess Scala calls them traits also, I think. And it's just polymorphism. So if you have, if a type is polymorphic in copy, what they call the copy trait, then whenever the compiler detects that a move is happening, instead of actually moving it, it copies it, and then keeps the original owned in the original place and the copy owned in the new place. So this is just a shorthand for things that are really small that you basically always want to copy, like ints, because there's no downside to copying an int. It takes exactly the same amount of space as the pointer that you would have had anyway, so you're all good. So there are a handful of these things. Anything can implement this, but mostly it's only done for very small things where it's not a big deal. and then it'll just copy, and then everything works out. So that's kind of nice. That's not really a big part of this, but kind of neat. So this is a similar thing to that.
Question.
Yeah.
As long as it's immutable?
Yeah, everything you've seen so far is immutable.
Okay.
Everything is immutable so far.
Sorry, mutable or immutable?
Immutable.
Immutable.
Everything so far is immutable. Yeah. Yeah. Yes. So this is a similar case to that case. Here I'm taking a reference to S. So I'm getting the address value of the pointer. And references are also small, so they also implement copy. And so I can pass a reference in multiple places, and I just have to declare this to take a reference. There are some rules about this, which I will get to, but essentially what's happening here is I take the reference and then I can pass it in, and now we're all cool from an ownership standpoint. Oh, I should show that compiles, because that's the point of this. Yeah, it compiles. Okay, so here's how it works. There's another trait called drop. And when you implement the drop trait, when your variable goes out of scope, and there's always a deterministic place it goes out of scope because it is always owned by exactly one scope, always, then when it goes out of that scope, the drop trait gets called if it has been implemented. And that does whatever it wants. So for example, there's this thing called box. A box is a chunk of heap memory. So I say box new this string. So it puts the string on the heap and gives me a pointer to it. And box implements drop, and what drop does is it frees the memory, not jump. So what happens here is this is basically my allocation when I do box new. And I pass it into example. Now example takes ownership of the box, and so I can't use it here. And inside, when it goes out of scope, at the end of example, it frees it, deterministically, no problem. I know exactly where the free happens. It's exactly where I would free it if I was the developer. And I'm disallowed by the compiler from doing this use here because the compiler knows that the variable will have been freed by that point, which is one of the reasons for the ownership system in the first place. So I can compile free, and that works. And if I try and use after free, then it says no. Use of moved value. Yeah? Does that make sense? Okay. So now, back to our references. So a reference is doesn't own the value it points to. This is checked, so they call it borrowing in Rust. Basically, when I take the reference of S, the thing that I pass the reference to takes ownership only of the reference and not of the thing that is referenced. And there are some rules around what you can do with references as a result of that. But that means that my allocation still happens out here on the box, but my free happens down here. So I can call this twice because it just takes the reference and then it deallocates the reference, which is probably just on the stack, so it's fine. And it does that for both of these calls, so the calls are safe to do, and it will let me do both of them. So that's borrowing, where the call, where whatever you're giving it to doesn't own the thing, doesn't call drop at the end, because it knows that the parent still owns it, so it will get free at the end. So you can see here this is looking a little bit like region inference, where the because but I did it manually. It's inferring a little bit, but I'm helping it a lot. I'm telling it, okay, this is borrowed, so it knows that the highest thing that isn't borrowed is the owner, and therefore that's the region it ought to live in. So that's sort of what you can see happening here. And so unlike the other one, that totally compiles, even with two calls. Yes. So this is just showing ownership is a bit more flexible, right? So I close over S here in my closure, and move the value of S into Y. And so that means that this scope takes ownership of X. Well, Y takes ownership of S, and then I already had ownership of Y. So I free here, which means I cannot call this twice, because it's going to free after the first call, this space. And this doesn't have to be space, it could be a file, or close the file, because it's just this trick, right, that gets called at the end. So it could be any cleanup code that you want. So you can see that 5 is fine, but if I try and call it twice, it's not fine. Here, use a move value again. Yeah. So that's nice. So this covers a lot of your cases, right? Because this works for, arbitrarily complex memory, right? Which is the next one. Should I just do 5?
Yeah.
6. Yeah. So I'm going to do a linked list. Because why not? So here's my linked list. I take in a value and a list, right? My standard list cons thing. I don't know why I call it a pen, because I'm dumb. It makes a new list, right? So my list, this will look familiar to anyone who's normally used to algebraic data types, but because of the fact that we're in a more primitive language, or like a more low-level language, I can't just put list here. That would be like an infinite recursive type, and it doesn't know how big that is, and so it would explode. Right? It would give me a thing about not implementing trait sized. This is like, I don't know how big this is, so I can't allocate stack space for it. But it knows how big a box is, and a box is the size of a pointer, so that's fine. So I just box the list, and now everything's cool. Yeah, so I have this data structure that's this nested set of different heap allocations, and ownership is moving back and forth here. So you can see here, I create this string and this list, and they're both owned by the scope in main, but then I pass them to append, so they get moved into append, so then they get owned by this scope here in append. Now I make this new list. Now this new list takes ownership of X, and of a box, this box takes ownership of X's, and then the new list takes ownership of the box, which means that essentially this new list has ownership of X and X's, which were originally moved into append from main. Now I return this value. So when I return it, it gets moved back to my caller. So now main owns it again in the return call here. So it's fine. So I can pass this ownership back and forth like this, which means that I can do pretty complex control flows on my data without ever actually using anything more complicated than the basic types that are given to me. I can move in and out. If I want to do this, I have this borrow thing available to me if I want to, immutably read something. But if I just want to, work with a single piece of data in a single thread, like a single flow, then it's no problem. There's no actual sharing happening or anything. The compiler checks that no sharing is happening, and I just move back and forth. And at the end, I end up with a list that main owns, and when main is done, it drops the whole list and all references deterministically right there. So I can get pretty big things, right? This to me, this tool is a little bit of a step above, where we went from assembly to C, we got automatic control of a stack-like system. This basically just binds the behavior of arbitrarily complex non-stack resources to the behavior of the stack scopes, which is all you need for, it's not all you need for everything, but it's all you need for a lot more cases than I thought. Like when I started out doing this, I was like, okay, I'll go run through the ownership stuff, and then I'll get to the more complex examples where we need all these extra tools. And they're harder to think of because most of the stuff that I would write on a regular, if you think about a map, right, you're gonna take ownership of the elements of the list and pass them into the lambda that you pass to the map, and then you'll pass them back out to the caller, and you'll just cycle them around, and then at the end you've got a new list whose elements and spine are all owned by the caller, and then you return that back out, and now you're Caller owns it, and it's all great. So as long as you aren't doing mutation, especially, then everything is super good. That's nice. There is, I should say about this one, about this case. So these references are immutable. So even though I've got a pointer to the thing, I'm not allowed to change the pointer or the thing. There are mutable references in Rust, obviously. It has mutation all over the place if you want it. The mutable references, they have a fun rule where you can, if I can do this, so I can say, takes a mutable reference. This is fine. Oops. The variable has to be mutable in order to have a mutable reference to it. That's a good thing to require. But if I do this, that's fine. I don't know if I'm going to come up with a good example off the top of my head. I didn't prepare this example, and then I thought of it. Anyway, they require that you not have two mutable references at the same time. So this one worked, again, because I had one, and then it was gone, and then I had one that was gone. But if I wanted to do, say, this really terrible contrived example, why would you write that there? No, you cannot borrow is mutable more than one time. So that's part of their data races stuff, right? You can't have a mutable reference more than once. You can have more than one immutable reference, though. That's fine, because it's safe. So if I did this thing, which is equally stupid but not dangerous, it will let me do it. You can say some warnings because I'm dumb, doing dumb things, but it totally complies. So that's a fun thing to do. And also, you can't do this. You can't have a mutable and immutable reference. Because these could be going, I could be taking the first X and sending it off to some thread, and the Y and sending it off to some other thread. It doesn't know what I'm doing. So it's like, well, you can't borrow it as mutable because it's also borrowed as immutable. So those are some of the data race checks that they have in there. Okay, so this is my linked list again, but showing more of the guts, and as a result, doing more cool things. So instead of boxing my list, because I boxed the list so that I could make it be a pointer, because pointers we know the size of. Well, we also know the size of references, because they're also pointers, to whatever. So I just say, I have a reference to a list, but I have to tell it something that I wouldn't normally have to tell it. I have to tell it how long this reference will be valid for. Because I don't specifically tell it that, it's polymorphic. I tell it is as long as quote A. Quote A is how long this reference will be valid for. And then I just say that that's a parameter, right? So in the same way that we had a type parameter A for what sorts of things go in the list, we have a type parameter quote A, which is a length of time that references might be valid for. And I don't care what length of time that is, it's whatever length of time makes sense in context. And I say a couple of important things. One, that A, the value we are going to store in the list, must last as long as quote A, and that the reference to the tail must last that long. And of course, I recursively pass that parameter on through to my tail. So I'm saying that everything in my list must last as long as everything else in my list. And nothing can last a shorter amount of time, or else it would be deallocated, and then I would have invalid stuff in the middle of my list. So my whole list must be the same amount of time. And then my append here, I can also take a lifetime and say, okay, my tail that you're passing in has to have this lifetime, and the new one that I produce will have the same lifetime as the tail that you gave me. Because obviously I can't make it bigger, because I could make it smaller, but there's no useful smaller thing in scope here to make it. So I make it the same. I say, whatever tail you gave me, I'm going to give you a new list that will last at least that long. All of its context. I'm not giving you a reference, I'm giving you an actual list, right? So it will last at least that long. And then I can just pass this reference straight in, and then my append totally just works. I have to take a reference to nil, so nil is created inside main, so it will last for main has ownership, and because I'm just borrowing it here, then it never moves, so main will continue to own it. So that's fine. And 2 also lives at least that long, because main owns it. So append is happy, it gives me back a new list that will last for the length of main. So this really is the region stuff, right? This straight up is the region stuff. I can have smaller or bigger scopes where I pass these lifetimes around, and they are inferred where possible. But sometimes in signatures especially, you often have to include them to make it really clear what all these pieces are, but then when possible it'll infer them, like I don't have any specified on this line. It just figured out like, oh yes, I know what all those pieces are already, so it's fine. And then at the end here, I've got a linked list that is entirely not, like I didn't do any extra heap allocations to make this linked list possible. It's just a bunch of stack memory pointing at each other, basically, because it knew where to stick it. So my return values from up here, come back out, and they have pointers to things, but it's pointers to things that I already own, so I know that they're fine, right? And at the end here, it's gonna just deallocate the whole mess. So it's basically the same as the other linked list, but I couldn't return this from main, right? But if I had some other function here that wasn't main that I wanted to return it from, I could do that as long as something that was passed into that thing had a lifetime that I could specify to be the lifetime of the return value, so that I would go up another level. I can't do this without an argument easily. I think I can sometimes, but it's hard because it's like what lifetime would it even, what does it unify with? There's some stuff there. But especially when you're doing something like this, where you're taking something and sticking it inside another thing, you actually always have this option. And this is, I could still box these things, right? I could still box this whole thing up and then take a reference to it and give it a longer lifetime or whatever, put it in a ref counter. There's lots of things I could do here to give it a longer lifetime than just main, but because it's polymorphic in the lifetime and not stuck to main's lifetime, then this will work with whatever it is. As long as all of the lifetimes are the same as each other. Then it just checks, okay, these things all live the right amount of time in order to be valid. Like if I didn't put this A quote A here, for example, it freaks out because I told it that the A goes into the sublist, but the sublist needs a quote A, and then it's like, well, some parts of this are different than other parts, so that's bad.
When you say time, is it good to think that in terms of like the scope main, or reference to the scope?
Yeah. So a lifetime is basically just you can think of it almost in terms of the end of a scope, right? A lifetime is the time when drop will be called, on this, which is directly related to who currently has ownership, because the ownership passes from scope to scope, so the end of that scope is the end of the lifetime right now.
So practically speaking, is A get implemented as a pointer?
Oh no, practically speaking, quote A gets elided at compile time. It's only there for compile check purposes, so the compiler can be like, okay, I've checked that everything here will live long enough, and since I know it will live long enough, we won't leak anything, we won't use after free, we won't have anything invalid going on. I know that, which means I know it's safe to call drop at the right point, which means we also won't leak anything. And so that's great. So I insert the drop to call the drop, and then I forget that I ever knew anything about it. It doesn't live on at runtime. Almost none of this lives. Nothing I've shown you so far lives on at runtime, and like the boxes do, in that I said box new, and so there is a new box. But none of the rules about like at runtime, there's no ownership tracker that's going, okay, I've received ownership. Keep track of that. Okay, now it doesn't do that. It just checks at compile time that the ownership is all kosher, and then forgets, and just generates fully performing code. Yeah, that's what it does. Other questions about this or parts before this?
You take is there notation for take the intersection of two lifetimes, or like this needs to last at least as long?
Yes,
as...
there is. If I had a quote B here, then I could say that my return is this. Yeah, that is a notation that we have. I have not needed it, but
so is that the maximum of A and B?
no, that would be the minimum.
Oh, the minimum.
Yeah, it would have to be the minimum.
Oh,
because
okay.
you can never live. Yeah, I think it would be the minimum, because you can't live longer than the shortest thing that you have, right? So if you have something that only lives as long as B, and something that only lives as long as A, and B is shorter than A, then you're going to be invalid at the end of B, no matter, like, you don't really care what A. And you just need this for polymorphous, like, if you don't know which one is longer, A or B, at this point, then you might need this, but then the caller totally knows, or the compiler knows when it's analyzing the caller, and it can choose the right one. Only one of them will end up being relevant to the compiler in the end. Yeah. Good. Other questions? Okay. So basically all of this stuff makes it so that you can't do like the read-write stuff with the no two immutable references makes it so you can't. Basically that by itself gets rid of data races, most of them, because you just can't write to something that someone else is able to write to or that someone else is able to read from. So that's good. And it gets rid of most of your day-to-day, like, mundane stuff. This is what I was trying to get at earlier with the whole silver bullet thing, is that, like, all of these other solutions are trying to say, what if we solved all of our memory management problems and all of our other resource management problems by introducing this new system that keeps track of everything? This system that I've shown you so far definitely does not keep track of everything. There are definitely situations, which I will show one of in a second, that this does not cover. But instead of just using the strong tools that are sometimes impactful on our performance to solve cases like this one, right? I mean, this all just works out. It's fine, right? And this is the sort of thing where people will say, oh, well, I can't, afford to have the garbage collector taking up all this time figuring out whether or not the string that I passed to you and then you returned back to me again is, still referenced. Obviously it's still referenced, you just gave it back to me, but the garbage collector is going to spend all this time looking at that. I can't afford to have that in my program, so I will write it in C and manually deallocate it myself. And Rust is trying to kind of give you enough tools in your toolbox that you don't have to choose extremes like that. You don't have to say, either I will need a garbage collector or I need to do every single allocation and deallocation myself. I can have some kind of middle ground where I can say, no, you know what, for like the 80% case of what I'm going to do in all the algorithmic parts of my program, I'm just threading the data in and threading the data back out, or maybe I let that guy read it for a while and then he doesn't actually do anything with it, and I let that guy read it, so we borrow here, we borrow there, and we move it back and forth, and then we're done. We don't actually need shared references for most of the data, right? There's always those key pieces of data that we do, and this doesn't handle that. But for a large amount of the data, we just have it. I give you the one, I give you the two, you add them together, you give them back to me. Like, why do I need a garbage collector? I don't understand what's happening, right? Yeah. Okay. So let's look at a more complicated case, which is way better than the more complicated case I was going to show you, but Chris gave me this one. It's awesome. I could have used something other than a ref counter, but it's a tool that is easily available to me and happens to solve the problem. So here, what I'm trying to do is I'm trying to create a closure that has some mutable state. So it's much easier to show this if you have mutation. It works without mutation, but I was trying to think of a motivating example that didn't have mutation, and that was harder. So this is using mutation. So I'm trying to set this space. I increment it when you call up, when you call down, I decrement it. But these are completely separate closures, right? That both own the same one mutable space, and that I can just move around arbitrarily, and who knows which one will get deallocated first, or if they will get deallocated at the same time. Who knows what will happen, because they both have ownership. And I will return both of these things, and then I just call them. I just got them out here, and I just call them. And they mutate up and down this thing. So first I will show you that this works. I compile it, and this one I will actually run. Look, stuff goes up and down. So definitely it is working. Okay, so this is, I have to, here, up here, I make my space a cell, which is just a mutable. Well, boxes are mutable, but as soon as anything you put in a ref counter, the words to describe this are a bit. So a cell has interior mutability, is what they say. So anything you put inside a ref counter assumes that its contents are immutable. But a cell is something where the cell is immutable, but the contents of the cell you can change, right? With this set call that you call on the cell. So it's mutable, but differently than like a variable being mutable. This variable is not mutable; it's an immutable variable containing a mutable object, which is a cell. That's what's happening here. So I stick the cell with the number 0 in it into a ref counter, and that makes me a new ref counter. And basically, the only thing that RC has implemented on it it's mostly transparent. RC it implements a special trait that lets it basically pass anything I try and use on it through to the contents to the cell, so that I can do things like just a.get and a.set here, which are operating on the cell and not the ref counter at all. But it implements one thing of its own, clone. So clone is like copy, except you have to call it yourself. And when you clone a ref counter, instead of doing a deep copy of all the data all the way to the bottom, it does a shallow copy of itself. It makes a new pointer and increments the ref counter. That's it. That's what it does. And then drop on RC is implemented as decrement the ref counter, and if you're at 0, then free the contents. Right. So I do clone here. Now up closes only over A, and it's a move type of closure. So A is going to move into up. Now up owns A, and down owns B. That's fine. The checker in the compiler is happy because each closure only owns one of the two things. Neither one of them is owned in multiple places. There's no sharing happening. No sharing at all. And then we return it, and then we use it, and it works out because while we aren't sharing anything the compiler can see, RC has inside of it, and RC is just implemented in Rust using manual allocations and deallocations inside of itself, right? That's how you have to implement primitive stuff, usually. I assume it's using manual ones, actually. I don't know. It could be using boxes and just a number. I don't know how they actually built it. I didn't look at that code. But yeah, so I don't have to use a ref counter here, but it's a tool in the toolbox that they provide that's very easy for me to just pop one up, and then I only use it in the places where I need it instead of using it everywhere. And this is a non-atomic ref counter, so this one does not use a lock around the number that is incrementing and decrementing, which means that if I try and pass it to a different thread, it will fail. Because you have to implement a trait that says you're allowed to be passed between threads. And there's a different one called ARC, atomic ref count, that can be passed between threads and always uses music. So there's a bunch of other abstractions like this. There's mutexes themselves, and there's channels, and there's vectors. There's a lot of these things in the standard libraries that they have, but this is kind of the simplest building blocks are like box and RC and cell. And instead of when Rust first started out, they tried to have like 16 kinds of pointers and 4 kinds of closures to capture every possible use case. And what they eventually learned was that it's way easier to just have the simplest set of building blocks, this ownership system and the borrowing system and the reference checker to make sure that you're not doing anything weird, and unsafe blocks. And then you can just build any abstraction you can think of. And so if we think of other ones, then it's fine, right? So you could have a garbage collector that only runs for things that you want. Once you're running a garbage collector, you're a host. So like maybe you should just use it for everything. I don't know, but you don't have to. You just give it some things, and most other things will just get handled deterministically because the system already can do that. So why bother doing anything else, right? Yeah. So that's kind of one simple example of basically you move past the constraints by using a low-cost abstraction. And it's much lower cost than a ref counter would normally be, not because it's magically a better ref counter, but because you're only using it on this one variable, and every other variable in your program is still being handled in a simple deterministic way, which is nice. I like it. Questions about this snippet, or anything I said, or anything at all?
So can you clarify that the reason this reference counting is lighter weight is because most of the time when the reference moves the compiler can statically determine that the number of references stays constant?
Right, that's also true. That's for sure true. The ref counter only increments when you call clone explicitly. And if you don't call clone explicitly, then you won't be allowed to move it, you won't be allowed to share it, because that will break the normal movement compiler checks. So it decrements only when you call clone explicitly, it increments only when you call clone explicitly, and it decrements only when that particular reference gets dropped finally. And any other referencing or dereferencing that happens, you'll probably just use, like you said, you'll probably just use a normal move, because you didn't actually need to share in that particular case. So you'll never have a case where you like increment it over here and then go over here and decrement it. That will never happen. You'll just move across that boundary, and you only increment when you actually need to add a new person who has ownership. Yeah, that's definitely true.
Okay, yes. That's what your description sounded like, but it wasn't completely clear.
Yes.
When you said that the RC, it would fail if you moved it across a thread boundary, you mean at compile time, right?
Yes.
Yeah.
Yeah, at compile time, if you try to fork a thread with a, like, usually you call fork with like a function of some kind, and then that will close over things or take arguments or whatever at that point where you're forking it, and anything you're giving to it has to be marked with a trait that basically says this is a thing. It has to either have the copy trait, in which case it'll copy it, or it has to be something that can be moved across the boundary, which is, like a lot of primitive things, will move across the boundary just fine, because there's no problem with that. But some things like RC will say, no, you can't move me over there, because there might be other clones of me on this side, and we're not atomic. Because you don't want to have a lock all the time in your single-threaded program, just in case you use a multi-threaded program, so they do allow either one here. And this cell is doing its safety in this particular case by copying. So when I call set here, it copies the number from this context into the cell. And then when I get, it copies out of the cell. And that's, so the cell is actually thread-said in that way. Yeah. So I can only store things of known size with a copy attribute in a cell. There are other kinds of mutable boxes if you want to do other kinds of things. Yeah.
What is your feeling about the complexity of language? I mean, to learn all these rules and keep them in mind.
Well, I am probably the wrong person to ask about that, because I don't find languages as hard to learn as other people often seem to.
So I'm a C programmer, and I have never worked with this language before. But based on Stephen's description, a lot of the things it does are things that I wouldn't have trouble figuring out, and the biggest obstacle would probably be letting go of my paranoia about the compiler getting something wrong and not learning how to use the management that the compiler offers.
Yeah, I think one of the key things about the building blocks in Rust is that none of these building blocks are new ideas, right? Having an ownership system is not a new idea. The new idea is making the compiler enforce the ownership system, right? Using, read-write semantics on your mutability to prevent race conditions, that's not a new idea. The new idea is that the compiler enforces that, right? If you go into any of the giant balls of terror that are C++ libraries, every single one of them has 1,600 different shared smart pointer implementations where they use tons of template boilerplate to make it so that you can have a lot of these kinds of semantics. They're just entirely optional, and you have to do them on purpose. And so sometimes it'll just not, you just forgot to do it, and then you don't have this, right, you don't have the guarantees that you have here, but you have all the same capabilities. So I think on that front, it's not too bad to learn the concepts, because there's nothing fundamentally new. It's like, I own the memory, now you own the memory because I gave it to you. Sometimes there are going to be cases where things are perhaps a little bit non-obvious. I mean, these are not the only features in the language, right? Like there's a lot. So for example, earlier today, I actually don't 100% know the answer to this yet. Well, I mostly do. So I tried to make this function return a boxed tuple of functions, and now it returns a tuple of boxes of functions. And the reason for that is that when I tried to put the two functions into the tuple, then the tuple said, oh, I don't know how big these functions are in order to keep them inside of me, so you can't do that, right? And so I had to put the boxes inside the tuple, and that's just, because the tuple has a fixed amount of space in memory that it takes up, and it has two spots for two references, and then I put functions in, and it's like functions could be, who knows what those are? Those are just big weird blobs of things that we'll have later. So maybe make pointers to them for me, which I did, and it was not a problem. But there's, I've run into a couple small things like that. This example, when I went to write it earlier, I tried to just declare the ref counter out here, and then maybe do the cloning inside, because that intuitively felt right to me. The problem then, though, was that as soon as I'm calling a.clone in here, then I'm taking ownership of A in order to clone it. And I owned A and the clone of A, and then I couldn't give anything to the other one, and that was not helpful at all. So I cloned it up here. If RC implemented copy, it would do that for me by magic, but that might not be what you want, because it might make more
accidental magic.
Well, it might make more references than you want, because it's not going to be moving it around, it's going to be incrementing the counter all the time, which is not really actually what you want. Because like in this case, I only make one additional copy. I have the original and one copy. If this had the copy trait implemented, it would make two copies, one for here and one for here, and then it would decrement the original copy at the end, which is what a normal automatic ref counter would do, but not what this code does. This code makes one fewer increment.
Yeah, so when I asked the question, I was meaning to master the language, and the reason is I watched a C++ conference where they had a panel with who's who in the C++, Rust, and D, and Go, and things like that. And the Rust people recognize that the learning curve of the language is steep compared with, if the C++, for example.
I'd say the opposite.
So these features don't, to me, feel like things that would make the language harder to learn. They feel like things that would just be there and mostly invisible while you're doing the basics, and when they start to become visible, you should already know enough about what's going on to understand how they work.
So what I think where the learning curve thing comes from, and I see this in other language discussions sometimes, is that people have been conditioned, I don't know by what, to think that when your compiler gives you an error, that is bad, instead of that being the whole point of compilers, to give you errors. And so, for example,
the whole point of compilers is to translate code. We just like compilers that have lint built in because you should care about those things.
Yeah. So, so for example, when I was writing this code, I got a lot more compile errors than I would have gotten if I had written this code in C++. Way more, and more often, which is the whole point. If I'd done it in C++, the program would not have been more correct the first time. It would just have compiled successfully and then not worked.
Or worked some of the time.
Or worked some of the time, or all these other problems, right? And so, I mean, C++ is probably the hardest language there's ever been to learn, except for maybe APL. But that's just because it's got so many obtuse and obscure features, right? Most C++ programmers don't remember that those features even exist. They just ignore them, and they just write the code happily along, and then sometimes there are errors, right? And so that's kind of it's sort of a trade-off thing. It's like when the Ruby programmers say that, oh, Ruby is so much easier to use because it doesn't have any of these things that you have to deal with, by which they mean it always is successful when you go run, as long as there are no syntax errors, you will not get an error, which is true, but then also your code just straight up doesn't work, which doesn't sound like an improvement to me in most cases. It doesn't even feel like an improvement. I have to maintain giant Ruby code bases all the time and the fact that I can't even rename variables without my entire application just not working anymore for months is troublesome. We end up with a lot of variables that we just keep the name and we put a comment next to it saying this name is stupid. This is what it really means, because that's way easier than changing the name. Right? And so I think that whether or not something is harder or easier to learn is sort of a matter of taste almost, depending on what people feel is the advantage. Like when you get started in Rust, it will feel more frustrating than getting started in, say, C, right? Because if you start in C, right, and you don't know anything, and you just start like, okay, so I allocate a big buffer, and I stick some string stuff in it, and I do some stuff, like, within the first hour, you got this program, it's doing the things, it's leaking all over the place, you're using after free, but technically it didn't happen to go away yet, so it's still working, you're overrunning all of your buffers, but like there was nothing there this time, so it worked out, right? And so like you're so productive, but that code is not really working, right? And then you run it tomorrow and it
nobody cares if your program crashes every time it exits because it's already succeeded.
That's right.
Yeah.
So like it'll run fine today when you wrote it, you feel super productive, and then you run it tomorrow when it crashes, and you run it the next day as part of a library in a larger system that runs for a year, and then you wonder why you have to have 600 gigs of memory in your box, and all kinds of ridiculous things. And whereas Rust, you'll get into it, and you'll be like, all right, I'm going to start this thing. You'll be like, yeah, boom, doesn't work, not allowed to compile, nothing is working, I don't know what these error messages are, Google the error message, figure out what's happening, learn about an entirely new kind of abstraction that I should have been using to get around this problem, learn about ref counters, learn about, queues, message passing queues for passing messages between threads, learn about all these concepts that, you didn't want to have to know about. And why can't I make global variables? So I can make global variables, but I can't make them mutable. I can't make them mutable, but not if they contain this kind of data. I'm so confused. Why do I have to do all these things? Bang. And it'll take you like a whole day instead of an hour to write the program. But then it will probably not leave memory, and it will probably not have race conditions, and it will probably not have buffer overflows, which are all good things. So, it will probably feel like it has a larger learning curve at the beginning. But what I would say is what it probably actually has is a steeper learning curve in that you have to learn more things before your code will run at all. But something like C has an equally or greater sized learning curve that it just takes you longer to realize is there. And so you still have to spend a lot of time. At Rust, you'll have to learn all this stuff up front, and now you've learned it, so you're kind of okay. And your code runs, and C, you will think you don't have to learn that much until, oh no, I have to learn this, and now I have to learn this. Like, I've met new programmers who actually will say to me, like, oh, I don't know why everyone says that, C is such a big deal, it's so easy, it's no big deal at all, everything's totally fine. I just, put in the thing, and put in the other thing, and then you look at their code, and they're not even calling free. They're just calling malloc, and not free anywhere. Which is, which works if the program is very short-lived and you don't allocate very many things. But it's just, because they just get into it and they look at some snippets online and they cut and paste and then they compile and it compiles and it runs and everything's happy, right? So I think it's...
Next time you find somebody like that, send them to me.
Yeah. So I don't think that you can ever really definitively answer whether one language is easier or harder or whatever. There definitely is a learning curve to Rust, especially because Rust is, for reasons that are interesting, largely attracting people from Ruby and Haskell communities. And if you're coming in from a background where you've never done systems programming and then you come to Rust, Rust is definitely a systems programming language, right? If your background is entirely in writing cute scripts, and then with gobs of garbage collector everywhere, and then you're like, oh yes, they say that it has mostly automatic memory management, it's great. And then you come in, and you just write like Ruby, you're going to get stacks of error messages out of the compiler because you're just going to do things, even basic things like this, where I put a boxer on my list, right? Someone coming in from something like Ruby is going to say, okay, or from Haskell especially, right? They're going to come in there and say, okay, so I got a list, it's nil, it's cons of A of list, no problem. The compiler will say, list is unsized. And they will say, what does that mean? What is a size? Why do things have size? Things don't have size, things just exist in the world, right? And so that's going to be very hard on them. And there are a lot of these people coming into the community, right? The guy who wrote the book on Rust is a former Rubyist. So there's a lot of these people coming into the community, which is good because that means it smells enough like a high level language that these people are at all interested, which is fine. But they probably have a harder time. A low level programmer learning that pattern matching exists is probably like, oh, that's a neat piece of syntactic sugar. A high level programmer learning that sizes of things in memory and references exist is like, what is even happening? Like I had a coworker at a previous job where I had to explain to him on a regular basis, like what a pointer was and why that had any because he just never encountered anything at all, and then he'd pull up some C code for one of the extensions and be like, I don't understand. Why do we need a pointer here? Why can't we just pass it around and have it be magic? And it's like, because there's always a pointer there. It's just invisible to you in your scripting language, right? So those people are definitely going to hit some walls, but those aren't Rust's fault. For the most part, they might be poorly worded error messages faults, but there's still concepts that you have to. Whereas if someone coming up from C is probably going to be like, oh, okay, like I mean, even you look at. Some of this stuff right in here, and you're like, oh yeah, I just take reference to this and I pass it in here, right? And the Rubyist is like, what? Why is that? How is that different from just passing it in? And the C programmer is like, oh yeah, no, I literally know what that sigil means.
We use that to mean the same thing.
It's okay, right? So
I think
that was a really long way of saying I don't know. I like it.
I think one of the other things with the learning curve, if you go back to example 1, I think, is that because it feels very much like C or C++, the people who already know C or C++, specifically I guess C++, might get to a situation where they write this code and it seems completely reasonable, and the fact that the compiler doesn't compile it is surprising.
Right, it depends on how you learn a language, right? Because if you learn a language by getting the docs, reading the docs, and then like going by example through some stuff and then being like, sweet, then when you get to this, you'll be like, oh right, I know about ownership. This is going to move the ownership, and then it'll try and move again, and that'll be an error. Like, and when you get the error message, you'll be like, I got it. But if you just are the sort of person who's like, copy and paste an example into my text editor, make some changes, try to compile it, the fact that this is a compiler error will be surprising to anyone coming from any language who didn't bother to read about the ownership rules in Rust first. Because it's not that the rules are complicated, it's just that if you don't know that passing something, like the first time I wrote some Rust code, I had a method like this that was implemented from a trait, so it was like thing dot something. And that dot something was consuming self. It was passing ownership of the thing I was calling it on into the method. And then on the next line, I tried to use the thing. It's like, oh, can't use that thing. It's like, what? What is even happening? If I call a method on this thing, then I'm not allowed to use it anymore? How is that even possible? Of course it's possible. Once you know the rules, it's not hard. And the rules are basically, like, I say the rules, but there's like one rule. When you pass in a value, it gets moved. Unless it implements copy. That's like a tiny corollary, which you can mostly forget about. It just does, right? That's the rule. But if you've never worked in a system where movement even happens, then yeah, the fact that you call example S and it works, and then you call example S again and it doesn't work, seems insane. It's like, what? I didn't do anything. There's no, like, and you're like, okay, well, are there any side effects in example that could have caused this? Nope. The example is empty. There's no code there. But cannot do it. So I can definitely see things like that being. It's a new concept, for sure, but there's not a ton of new concepts in Rust. It's just that depending on which language background you're coming from, different ones of the concepts will be new. And the way that the syntax is applied might be new, right? Like there's no syntax that says the movement happens here, because movement always happens, so they don't bother to mark it, interestingly.
So the ways around, the ways to run this twice. Mutable, you can copy it, you can explicitly copy it.
So you can copy it, you can give a reference to it,
right.
Or you can have the thing you pass it to return it again. so that you get ownership back, right?
Okay.
I could do this, and then this. This is fine.
Okay.
So I can pass ownership, and this is what I did in the last linked list example, right? I pass ownership in, it does things, and passes ownership back, right? You're passing your ownership back and forth, and this can be between multiple functions. You know, you can thread it around, thread your ownership around, have it end up back at the top of the end. That's all fine, right? Or you can use borrows so that if there's no, because returning exactly the thing you passed in is probably a code smell. Because probably you wanted to do this. Because if you're returning exactly the thing you passed in without changing it, that means you're not mutating and you're not building something new based on it. So probably you're just reading from it, so you just used a reference, and then reference is that's totally safe, right? So this would be the idiomatic way to fix that problem, but you could thread it in and out, that's totally valid in the language. And that's what you would do if you're passing it in, building a bigger data structure around it, and then passing that back, right? That's how you would pass ownership in, give the ownership to the bigger data structure, pass ownership of the bigger data structure back. That's totally legit. You're allowed to do that.
So let me just jump in here. It's my fault, but we're kind of over time. So you can let people escape if they wish to escape. And,
Yep.